Hello everyone, welcome to Aerospace Engineering lecture series by Gate Partner. I am Abrar. Today we will learn stream function, streamline and their importance in understanding fluid dynamics. Of course, stream function is related to streamlines. What I have on my screen now is a picture of a great mathematician who introduced the stream function. The stream function was introduced by a French mathematician Joseph Louis Lagrange in 1781. So before we begin our understanding and the physics that stream function relates to, I want you to know what is continuity equation and how we are going to use it. So in general, continuity equation is given by dou rho by dou t plus del dot of rho v bar equals to 0. Fine. For incompressible flow, rho is constant. Let's take rho as C, where C is a constant. It relates to change in density, d rho equals to 0. So the above continuity equation, if I write again, dou rho by dou t plus del dot of rho v bar, which is divergence of the velocity vector with the density, is equals to 0. In this equation, if the density is constant, this term vanishes irrespective of whether the flow is steady or unsteady. Here the main concern is density is constant in an incompressible flow, and we can pull out this row out, so giving rise to del dot of v bar equals to 0. It is very commonly written as div of v bar, that is divergence of the velocity vector equals to 0. If we write this as I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z dot at the velocity vector whose x component is u, y component is v, and w component of the velocity is z component of the velocity is w equals 0. If I take the dot product with this, I'll be getting dou u by dou x plus dou v by dou y plus dou w by dou z equals to 0. Let's name this equation as equation number 1. Remember, this equation 1 is applicable to, just bracket this, it's one very important equation. So you can use this equation for, it's applicable to incompressible 2D flows. So for 2D flows, 2D the two incompressible flows, the continuity equation reduces to dou u by dou x plus dou v by dou y equals 0. The stream function psi is 1 which satisfies the following equation. So I would like to write a stream function psi is 1 which satisfies u equals to dou psi by dou y, v equals to minus dou psi by dou x. If I substitute this in above equation, let's name this equation as equation number 2, because I already used the equation number 1 to the above. Okay. So if I substitute these two components of velocity in above equation 2, I will be getting dou by dou x, dou psi by dou y plus dou by dou y of minus dou psi by dou x equals 0. So it automatically satisfies the continuity equation. So thus we can find a stream function psi that meets with the above two equations, that is u equals to dou psi by dou y and v equals to minus dou psi by dou x, and the continuity equation need not be solved. For the rest of the course, we will be invariably describing flows with a stream function. So let's talk about line with psi equals to constant, and I'm going to label that as constant c. Okay, just underline this. Fine. Let's go ahead. If along that line psi is equals to constant, that is, I can say d psi equals to 0. Okay, giving dou psi by dou x. So before we begin with writing back, if I write psi as a function of x comma y, I can write d psi equals to dou psi by dou x into dx plus dou psi by dou y into dy. And along the line with psi equals to c, this gives us 0. If I substitute in place of dou psi by dou x minus v dx, and in place of dou psi by dou y u dy, I get an equation minus v dx plus v dy equals 0. So from above equation, we get one interesting thing, that dy by dx is equals to v by u. It is the ratio of component of the velocity in y direction to the component of the velocity in x direction. So this is the slope of the line with psi equals to constant. Okay, so let's bracket this. It's again a more important equation that I will be discussing again later. So let's name this equation as equation number 3. Okay, so now if I consider a line along which psi is constant. Okay, and I choose an elemental length, let's say ds, like this. Okay, ds, if I write ds bar as dxi cap plus dy cap, which is a change in position. So this ds can be written as dx dy. Okay, and we just now proved that dy by dx, which is a pencil. We just now proved that dy by dx is equals to v by u. This is the slope. If I mark this angle as theta, tan theta equals to dy by dx is equals to v by u. And if I draw a vector over this, let this be the vector which is, and I define this as u and this as v. This vector, by definition, should be the velocity vector. Okay. What we have proved that psi is constant in a line of streamline of the flow. I'll come to the definition of streamline a little later. Right? Now let's look at what is this word streamline is all about. Okay. Streamline is an imaginary line in a flow tangent drawn to which gives the velocity vector. Alternatively, you can say that a line tangent to the velocity vector always is a streamline. Right? So let's look at what is this streamline is all about. Okay? So let us consider a three-dimensional axis frame. Draw a small three-dimensional axis frame. We have x, y, z components. Let's say there is a streamline which is flowing like this. So if I draw tangents at these points, I must be getting the velocity vectors. Hope you understand that these velocity vectors need not be constant in magnitude as well as in direction. They will be changing. They might be changing or they might be constant depending on the type of flow that you have. So let's choose a position vector R. Okay. If I move a little distance, dr bar will be a position vector on this. The fact that the velocity is tangent to streamline, so I will write this. The fact that the velocity is tangent to a streamline allows us to write v bar cross dr bar equals 0. Let's call this equation as equation 4. So guys, hope you understood that the equation of streamline in vector form is obtained in equation 4. So let's go ahead. So if we want to write for 2D flow, the cross product of the above two vectors v bar plus dr bar can be written as dx dy 0, since we are taking 2D equals to 0 and k cap into u dy minus v dx equals 0. That is dx by u is equals to dy by u, which is the equation of streamline. If you recall, dy by dx with psi equals to constant is also given by v by u. Let us denote slope of streamline with a variable m1 is equals to dy by dx is equals to v by u, which is also the slope of the line with dy by dx with psi equals to constant. Okay, so I hope you understand that the equation of line with psi equals to c is nothing but the streamline. That is, along a streamline, psi is the value of psi remains constant. Now let's extend our understanding towards what the difference in psi between two streamlines will give. So let's go ahead. d psi between two streamlines. Okay, let's underline this. Okay. Let us consider volumetric flow through small element. So before I bring that thing up, allow me to draw two streamlines. Let's say I have two arbitrary streamlines. So if I choose this to be the streamlines, obviously if I draw tangents to that, I must get the velocity vector, and along each streamline psi must hold a constant value. Let the psi value be a constant c along the line 1, and let psi be equals to d along line 2. I have two streamlines here. I will consider a small element ds. So let ds be the length of this element, so that if I am going in arbitrary direction s, ds bar can be written as dx I cap plus dy j cap in a 2D flow. So I can write ds as dx dy such that this angle I can call it as theta, and I can write tan theta equals to dy by dx. Okay, this region. Okay, my region of interest is now this. Fine. So let's look at what is happening through this face. So through the element dy, there is this flow going out of this dy element along in the direction x with velocity u, and dy into 1 is the area, and the flow going through this face is going with the velocity v, and the area is dx into 1. So I have those two elements here and here. There's u dy and there's v dx. Okay, so let's go ahead. So if we consider the volumetric flow through a small element of thickness ds placed on a streamline as shown in figure, the volumetric flow rate, the volumetric flow through this ds element is given by dq equals u dy minus v dx. Hope you understand. In y direction, we have the flow rate in the direction opposite to the y direction. That's why we have minus v dx here. Okay, let's go ahead. Okay, I can substitute in place of u dou psi by dou y to dy minus, in place of v I can substitute minus dou psi by dou x to dx, which can be written as dou psi by dou x into dx plus dou psi by dou y into dy, fine, which we know is equal to d psi. Therefore, we have dq equals to d psi. Above equation indicates that the volumetric flow rate is proportional to the difference between stream functions between two different streamlines. So if we now integrate this equation which we obtained above between two streamlines, we have q equals to 1 to 2 dq is equals to, at streamline 1 I have stream function defined as site 1, and it's along streamline 2 I have it defined as site 2. This side will be written as site 2 minus site 1, which is d minus c. Fine. Let's name this equation as 5. Okay. So let's discuss a little more about stream function, because in the course of study, instructors or in competitive exams or in interviews, they might be giving you velocity components in polar coordinates, in cylindrical polar coordinates. So let's discuss stream function in polar coordinates. Okay. The velocity components in polar coordinates are related to the stream function by Vr is equals to 1 by r dou psi by dou theta, and V theta as minus dou psi by dou r, where Vr is the radial component of velocity and V theta is the tangential component of velocity. So velocity vector in polar coordinates. Okay, so I'll pause for a while so that you think, do you really know, or how do you define the velocity vector? A very common mistake that most of the people do is they write V bar equals to Vr I cap plus V theta j cap plus Vz k cap, and they write mod of V bar equals to under root of Vr square plus V theta square plus Vz square. So this is correct, but is absolutely wrong. So it's a stupid equation where because if we look at the root of basic vectors, I cap, j cap, k cap are the unit vectors in x, y and z direction. How can you use it for radial, tangential and the axial directions? Which will make it very wrong. Okay, so the correct way of defining the velocity vector would be the velocity vector in polar coordinates should be defined as Vr, Er cap plus V theta, E theta cap plus Ez, Ez cap. Okay, which is absolutely the correct equation. And in fact, you can write the magnitude of the velocity, that is mod of V bar, as under root of Vr square plus V theta square plus Vz square, where Vr, V theta, Vz are the radial, tangential and the axial components of the velocity. Okay, this is a very important thing. Here we have a flow around airfoil. If we attach our reference frame to the airfoil appears stationary and the fluid appears to be flowing towards right, as shown by the red velocity vectors. Streamlines are lines that are tangent to the velocity vectors of individual fluid elements. Let's look at the velocity vector of an individual fluid element and decompose the velocity into x component and y component. We write the ratio of v to u and substitute dy by dt for v and dx by dt for u. The dt's cancel out and we are left with dy by dx. Rearranging equation, we obtain dx over u and dy over v. Had we examined the z direction as well, we would find these ratios also equal dz over w. If we know the velocity components as functions of position and time, we could integrate these equations to find the streamline passing through a given point. As you can see, the velocity vectors on top of the aerofoil, the magnitude of the velocity vector is increasing when it passes over the airfoil, and as it passes under the airfoil, the velocity vectors are decreasing. Okay, so if we look at this center line, the fluid particle is coming to a stagnation state at this particular point. Okay, so here we have a stagnation state. The definition of a stagnation state or a stagnation point is the flow must be brought to rest in an isentropic manner. So we'll talk about this little later. Okay, so the equation that we obtain now, this equation, okay, this equation can be applied for finding the equation of a streamline. Okay, so we can, if we know the velocity components as function of position and time, we could integrate this equation and find the streamline passing through a given point. Okay, let's look at how the streamlines would look like through some of the examples of fluid flow over certain bodies. Okay, I'll take flow over an airfoil. If I draw and streamline one of the streamlines like this, we can see that this streamline is not changing with time. So this is the case of an steady flow. So particles are changing the position, but it's not changing, the pattern of the streamline is not changing with time. So it is not an unsteady flow, it is a case of a steady flow. Fine. So there can be several examples like this. If I visualize this streamlines by using a virtual wind tunnel model, okay, so I see the clear pattern of the streamlines. It's a very good visualization too. So hope it gives you a clear idea about how the streamlines should look like. We can insert as much smoke as we want in this virtual wind tunnel. Okay, this kind of tools helps us to visualize how effectively different bodies would work. Okay, so I hope the lecture was helpful to you. If you like us to share more videos and create more creative and interactive sessions like this, please subscribe to our Gate Pathshala channel and like us. Thank you.